Soccer.
Football is correct, I think, but people's opinion changes. You can still see that, right?
Yep.
Perfect. Yes. Well, hello everyone. Today the paper we're presenting is about TacticAI. It's a paper by DeepMind, and they were partnering up with Liverpool Football Club in order to bring data, modern machine learning into the realm of more traditional sports. I can't. Can you see the top of the slide? It's I think it's slightly hacked for me, but can you see that?
Yeah, we can't see the title, but we can see the GIF.
Yeah. It's I think the sharing. Oh god. Yeah.
Oh, whoa, what happened?
Never mind. Okay. Yeah. What's the issue that people try to solve? Well, in the last couple of years, almost every sport has had a data revolution of some sort, right? You have much better tracking systems if you think of baseball or cricket, where you can actually now say follow the ball exactly where it goes, at what speeds, at which angle, at which spin it goes, and that led essentially in every sport to a flood of new data. And especially in sports where there is a very dynamic element where people essentially move all the time, begs a little bit the question what to do with the data, how to actually resolve this very rich data, massive movies essentially of players moving into something that is an actionable insight. And in this particular paper, they were focusing on corners. Why? Because corners are set pieces, meaning they come reasonably often or appear reasonably often in a game. They are, things stop, people move into position. So it's sort of repeatable in a sense. But this, like corners in particular, are also very goal relevant in the sense that corners often do lead to shots, and then shots often lead to goals. So it's something where a team can actually practice in order to make their chances of winning better. And I don't know how familiar you are, but there has been long debates in the past, and there were common misconceptions about corners that led to small teams actually overperforming compared to their budget by just exploiting weaknesses in other teams' corners. So that's why most football clubs are quite invested in having like corner specialists that practice that with them. Let's see. In this particular paper, so what is the raw data people are working with? Well, they have spatial temporal data of the players, essentially where players' position is, collected at 25 hertz. So very small time steps. You see where everyone is. I don't know how they actually collected it, but I suspect it's done via tracking chips rather than reading it off from a video stream. But it's hard to tell, and this data is usually not quite straightforward to come by. They have event stream data. I suppose that is manually collected. Is essentially where people say, okay, this player made a pass to that player, and then a couple of seconds later, okay, this player made a shot at goal and it passed, or it missed completely. And that sort of data is fairly common. Again, you usually would have to pay to get that. And what other data they have? They have who's in the lineup of a particular game or situation, and who are the players involved, and some of their physical attributes, and generic game data, right? So what's the size of the pitch? Where are they being played? I suspect they have also stadium information about like what is the capacity of the stadium, how many people are in attendance, though much of the data they just didn't use. And then they process the data. They chose corners, and they essentially took.
Arvind, is any of that data, like the spatial temporal data, available to people for free? Like, could we have access to it during the game?
I don't think so. So the reason is it's actually a very good question of who actually owns the data. To some extent, is it the people in the stadium that provide the technology to get the data? Is it the clubs themselves? And there have been cases in the past where players argued actually the data is theirs, and it's to some extent sensitive because they have often also trackers for the physical stats like heart rate, and so it gets quite medical. So and medical data is intensely private, and there is very strong restrictions on what you can share. So I think for some some seasons, typically there are some samples of data. I think for Premier League, I think you would probably find somewhere a bucket where these data providers would offer some. I think Skill Corner is one. They do video feed analysis and sort of backtrack from the video feed where players are and do some Bayesian smoothing around that. And there you can get samples, but it will only be for a select few games. But then again, even 1 or 2 games are plenty of data to get your hands dirty with. In this this particular study, so what they did was they took because they really only focused on corners, right? If you think about if you sample at 25 hertz, you get a massive amount of data frames if you want, but they only selected over the whole season these 7,000 something corner kicks, and they did that by matching the event to the moment where the ball is leaving the foot of the player. So you can also argue that there's already some bias in there, right? So if a player is already moving in a certain way, I'm sure that the model can pick up quite a lot of information about that is a bit more of the decision in the making than a prior decision, but that's just a detail. We have the player positions, of course, but also the derived velocities, and they're normalized and scaled. And it's really annoying that we can't see the titles here. Title is essentially what is the what are they actually trying to predict in order to improve their
you can see the bottom half, so it's like kind of guess.
That's yeah. So it's like the important tasks. One of the tasks they try to solve in this data set, or with this data problem, is who will receive the ball, right? So you start at the corner, you know who is essentially kicking the corner, and who are they actually playing to. From there, the next thing you try to predict is whether a shot was being made. So in this particular problem, they're not really looking for how good a shot is, right? Because you can argue that certain shots that are, say, closer to the goal with no one in front of you are more likely to lead to a goal than shots that are further away and where there's a lot of crowds in the middle. But they didn't care so much about that. They really tried to answer the question, is there a shot, yes or no? It turned out when they did the preliminary study that when they just tried to build a model on the data that was supposed to predict whether there is a shot or not, that model was essentially as good as random guessing. And they figured that if they split the problem into these 2 separate sub-problems, finding out who is going to receive the ball and whether the guy, if he received it, made a shot, is sort of the same problem. I think you can just write it as a formula like this, yet it vastly improved the model. So that's actually a very interesting question of why that is. Why can't the model train it a priori if it's exactly the same data it receives, really? And lastly, of course they're working with this Liverpool Football Club. So the question was, can they use this model to actually make recommendations to players that help them make better decisions or better behavior? And better behavior in the context of corners means, of course, when I'm in the attacking team, I want to increase the probability of a corner leading to a shot. If I'm in the defending team, I want to decrease the probability of the other team having a shot. So, and the model is supposed to give adjustments to whatever's the current position of players that are active to improve these metrics, essentially. Now, the decision was made to use actually a graph neural network. Now, some of you might have been in my other talk on football, and there they used a fundamentally different architecture. And in the old one, they essentially had the pitch, the soccer pitch itself, cut into like a grid of like 1 meter by 1 meter squares, and a player would essentially be a 1 in that grid and zeros everywhere else. Whereas here they actually decided to go into a graph architecture where every player is a node, and in this particular case, every player is connected to every other player, whether they're on the same team or not. So they form a dense graph, and on each graph node we have a certain number of features. So as we mentioned before, that the player positions and velocities. We have whether the ball is in possession of a particular player. And we have the heights and weights of a player. Heights and weights is sort of important when you think about if you have like a crowd of players, you have one player that is considerably taller than the others. It's probably a lot easier to play the ball to him. He can easier receive the ball, or if they are heavier, they also can easier move other lighter players away. There are edge features. Interestingly, only one, whether the connection between two players, whether they are on the same team or not. And later they have the global features for the receiver and shot prediction of who received the ball and whether a shot was made or not. But these are not sitting on a node, which is kind of interesting because you could easily think of the receiver statistic as a node-wise feature, but here they did it on a global level. Any questions at this point? Sorry, I'm not really pacing myself very well.
Not for me.
Very good. Then, yeah. So the really annoying, but let's see. So the model is essentially blind to the identity of a player, and you could very much argue that that is a fundamental weakness of the problem, right? So if you imagine you have Messi on your team, the fact that you know that he's Messi probably will affect how you would whether you want to play to him or not, right? But the model doesn't know that. But it's still quite comprehensive in the sort of data it has, especially the positions and velocity, which are arguably the most important things. Yeah, the features then are split in for the different tasks, right? So if I want to only predict who is the receiver of the corner, I only have the node features and the edge features. When I have the shot prediction, the model needs to know whether who has received the pass, so the corner pass. So I suppose that is also one of the reasons why they put it as global features, so that you can essentially use the same data set to train all of these rather than having to work on some masking. And it's essentially what the same is for the guided generation. In the guided generation, you also sort of have a S feature, whether the shot was successful or not, because that will later on be quite important when you want to adjust your positions based on whether a shot was successful or not. Again, as a defending team, you don't want the shot to be successful, so you have a slightly different context than an attacking team. Yes, let's quickly recap what the basic graph neural network architecture is. We have graphs. Graphs are made of nodes and edges. What the nodes themselves actually just form a matrix, right? So each row in that node would be one football player with k features, which is again position, velocity, and weights, heights. The edges, they could either be tuples, just saying like we have player 1 and player 15, they have an edge between each other. We could write that as an adjacency matrix, which is zeros and ones, so 1 if there's an edge or 0 is not. In this particular case, because it's a dense matrix, probably be ones everywhere. An alternative way to think of edges is if edges actually have features. In that case, edges become a tensor, right? So it's we have two players that are connected, so we have to have a dimension for the nodes. So node 1 connects to node 2, but then also we have L edge features. And in this particular case, it's just the one feature, whether this edge belongs to team members or opponents. And what does a typical graph neural network layer do? Think about it from calculation or message passing perspective, but each node, which in this case would be the player, formulates what message it wants their neighbors to know. Then they send the message to all the neighbors in their outgoing neighborhood. They receive the messages from all the nodes in their ingoing neighborhood. Of course, in this particular problem, because every node is connected to everything, these are the same. So you receive from everybody, you send out to everybody, and then you try to make a prediction on that node that you then pass on to the next message, or you sort of collect all the incoming nodes, incoming messages, think it through if you want, and then send it out in the next step, and so on and so forth. And that happens in layers and can be as often repeated as you want. Generally, okay, let's cut off a little bit. Generally, the most generic form of this in mathematical notation is something like this, where you have it's essentially an update equation, right? So Hn is the embedding or representation of the of the U node after n steps, and it's a form of two functions. You have the inner function, which is essentially the messages that are generated between two nodes, right? So psi is the message between node U and V, takes into account what is the edge information and the global information. We have, and that these messages essentially come from the neighborhood of a node. Then they are collated. So this operation that takes different messages and combines them is also network specific. So different architectures have different forms of these. The sort of important bit is that these are symmetric in a sense that the order of the node shouldn't matter. The reason is that the node ordering in your network is sort of arbitrary. It doesn't matter whether you start counting the opposing team first and then the attacking team, or the other way around. That order shouldn't matter. And in order for that to be true, this collation operation has to be invariant. So essentially, if I go back, if I take my feature matrix and just shuffle it around and keep the adjacency matrix consistent, the outcome of my calculation should be exactly the same. And for that, this collation operation has to be symmetric. However, that is in some operation actually not quite true. There are actually versions where you sort of have an approximate invariance, and that sometimes works actually also quite well. And then you have this other function, this quote unquote thinking function on a node that takes all the inputs, weights it up against the own representation, and then comes up with a nonlinear change to that updates the presentation. Are people so far comfortable with that? I mean, that is something we essentially had quite often in the past before.
Yeah, makes sense to me.
Perfect. Now, in this particular case, they choose an attention mechanism, where what it means that this function sort of decomposes into each node message that essentially only depends on the node itself, and an attention function that essentially weights the different nodes against each other. Yeah, if in this particular case they shows GAT v2, which has this form. You take for two nodes, you have these weight matrices for each node representation, a representation of the edge, a weighted form of the edge, and the weighted form of the global features, and they are all concatenated together, and a leaky value on top of that, and a trained parameter on the outside. Now, in traditional GAT v1, this A vector would be on the inside, but actually that turned out to have some very serious flaws. So this version where the vectors on the outside is actually much more generalizable. And as you can see, this attention mechanism makes use of the node features. So not all graph neural networks actually do make use of the node of the edge features, but this particular version does. So that's why it's used here. It's quite powerful. Now, technically, there's a bit of a weighting actually between the different nodes, and these attentions are typically just numbers between 0 and 1, right? So it doesn't do anything complicated to the node messages themselves. It just combines them, really. Now we come to the sort of.
Sorry, can I ask a question before we continue? Hello?
Yeah, please.
About GATs.
Hmm?
Is attention here between all possible nodes?
Yes.
Or how do
this,
you use the graph then?
say again?
If it's all between all possible nodes, how do you use the graph itself?
I'm not quite sure what you mean by use the graph.
The graph structure, right? Because if you have a GCN, you would only account for you would do message passing only between neighboring nodes.
Yeah.
But here with GATs, it's more like a general question. about GAT?
It's still you still only sum over the node neighborhood, right?
Okay.
So
attention only across neighbors.
Yeah. Why I say it's
every node is connected to every other node. So it's
in this particular problem, right? So this is like a for this particular problem, they chose to connect every node to every node. So that's why here it's the same, but generically that's not true, right? So generically this would still work if you don't connect every node to every node.
Then why do you have a GNN then? If everything is connected, then if it's a fully connected graph?
Very good question. We will see later that for some reason it does make things better than using just a perceptron or multi-layer perceptron, right? And I suppose that this is a convenient way to actually get the edge information in. And
yeah, it's also MLP wouldn't allow message passing.
Yeah,
so
but
you want some sort of attention.
I think concatenate all the node and edge information into one big feature block and try to run that through. It's just, for some reason this seems to be fairly efficient. What's actually quite interesting is that the edges are actually also quite simple, right? So it's just a binary feature rather than containing information like how far players are away. Because you would think that, especially if you think of pass acceptance, how far away the other player is probably quite an important quite an important feature, but they didn't. Why they didn't really say either. They just say that they did. So.
So is it only one GAT layer then?
No, in this particular layer, in the final model, they have 4, I think.
Okay, to allow access to.
Yeah.
It's also funny because they already have access to all neighbors, right? To all nodes in the graph. If you have 4 layers.
Yeah. Well, you probably do need, but because if you have only one step, yeah, you could argue that sort of the order of messages, how they come to your player and ultimately to a player that would likely make a shot contains these additional neighborhoods. So you would think that the depth does matter, and I'm sure they tested that smaller graphs just don't have the power, right? You need
maybe it allows you different, more granular attention between nodes because if you, maybe because. Can you imagine if you have multiple hopes and then you can pass information through those hopes and then not pay much attention to the immediate attention, I guess.
Yes. And also what possibly is important, so you have actually multiple attention heads. I think they use in the final model 8 attention heads. So especially given that you only have 7,000 something data points, it's actually quite a lot of parameters, you could argue.
Yeah. Cool, thanks.
No worries.
One quick question. Yeah. The 2 straight lines between the matrix multiplications.
Here.
What is that?
So these are concatenations.
Okay, so they're basically making sure everything's the same size, concatenating it.
Exactly.
And then putting it through leaky ReLU, and the A is the attention weights.
It's also a learned parameter, almost like W, except that the A in this particular case is a vector.
Okay.
And the paper that actually proposes this GATV2, I think that is a really nice paper to actually also present. It's short. It's only 3 or 4 pages, I think, but they have a very nice toy problem where they show that putting the A outside of the leaky value makes a massive difference to what the network fundamentally can learn, and makes it truly actually generalizable.
Okay, interesting.
Yeah. Any other questions? No, then let's go on. So now we come to the most important part of the paper, or what perhaps the most interesting, is that they consider symmetries. So they say in this particular problem you have asymmetry given a corner. Corners can happen on both sides of the pitch, and you would expect that if So if I were to flip the pitches around exactly, it should be the exactly same problem. So any probabilities I derive should be exactly the same. The same as if I were to flip top and bottom of these pictures. So they essentially say I can take any situation for a corner, and I could I have three other ways of flipping it, and we know that should be the same. Now that is a bit of an assumption.
I disagree with that.
You're probably right.
Just because of like right and left footed people and then crowd noise.
Yes, that's you're absolutely right, because now crowd noise, you technically don't know where the crowd is, so you would expect that to average out, but because right and left footedness are not evenly distributed, you're absolutely right that there would be a bias. Now technically you could, if you were to know the footedness of each player, you could add that as a feature and add that to that transformation. Then when you say we flip left and right, when we flip left and right, what do? We actually flip the x coordinate around. We flip for all velocities, we flip the x component around, and we could, in principle, actually, I'm not sure whether footedness is that easy to transform. Probably not. Otherwise, they might have added it. Actually, now that I think about it, it might not be. It might change the symmetry group altogether.
Yeah, it should just be a feature, right?
Again?
It should just be a feature. Like your
Yes.
skill on the right foot, your skill on the left foot.
Yes. The question is, right, if I flip left and right, then that feature would not be flipping. If I were to flip up and down, technically I would flip it, but it sort of depends also whether the
you can't flip it, because then you don't have the player with the same skill on the left foot as on the right foot.
Yeah, but if you flip the whole situation around, say a player moves in onto the goal via the left lane, and for him, I think being left-footed, I think gives a disadvantage versus being right-footed, right? So because you can easier shoot.
Yeah.
And so you would expect that if you flip the situation around, if you have the same player running on the right lane, but then flip his foot to the left side, that possibly would be the same. Whether that actually fits in nicely with these transformation, I'm not quite sure. Now we make a bit of a step. So these are symmetries, right? So and what is a symmetry, or how can we represent a symmetry mathematically? That is the question. And for that we need groups. And what is a group? A group is essentially a set of elements that have an operation to it that is closed, and you have the identity, you have an inverse, and for each element, and the group is associated. So what does it mean? Closed just means that if I take any two group elements and combine them, I get something that is still in that group. If identity means there is an element in that group that commutes with every other element and just leaves the element the same. And the inverse means, if I take an element and I take their inverse and I combine them in this group operation, I get the identity element again. What are common examples? The whole numbers actually have two quite common known groups. So it's the addition. In addition, you can add any two numbers and you get still a whole number out. The identity element in the addition is the zero, right? If you take any number and add zero to it, or zero plus any number is still that number. And for every number, you have just minus that number as its inverse. So can take 2 plus minus 2 equals 0, which again is our neutral element. Another common group is the multiplication group, where the neutral element is the 1, right? So any number times 1 is still that number. So 1 is truly the identity element. Any number, I think I'm saying, I think we have to be careful there, but there's ratios. I think ratios we have to be, because the inverse of numbers is a ratios. Never mind. Take the addition as a good example of a group. However, that group is infinite in size. Now the idea is that every symmetry group, such as this, also follows such a structure in the sense that I can take any of these operations, combine them, and still get a operation that is as part of these four, right? It's obvious if I don't do anything, our identity is just not doing anything. But flipping it around, for example, twice, we get the identity back, and the identity is part of the group, so we're good. Or flipping it from left to right and then flipping it top to bottom is the same as just rotating by 180 degrees. So associative just means that this. Oh, bloody hell! I'm a bit annoyed that I can't see everything. Typically, how you deal with these, you write a group table. Essentially, a group table tells you how every element behaves when you combine it with another element. Right. So here we would see left, right flip, top, bottom flip. If we take them together, we get exactly the left, right, top, bottom flip. We see that the identity is on the diagonal. So every group element has its own inverse, which is just itself. So identity times identity is identity, but top flip twice is again identity. And this group is called the dihedral group, or D2. And it has essentially the same symmetry as a planar square. So I can take a square, and if I flip it top to bottom, it's still the same square, or if I flip it left to right, or to both of these. That is a bit of an abstract leap. People are so far comfortable with that.
I'm wondering one thing. Are you trying to create symmetry or break the inherent symmetries, the invariance in the GNN?
That's a very, very fundamental and very good question. So the answer is probably yes. So we know there is a symmetry, and now the question is, and that is, we're going to come to that in a moment, the idea of deep geometric learning, or geometric deep learning, is the study of how can we, if we know there is a symmetry of a problem, how can we incorporate that symmetry in our neural network to make the neural network as efficient as possible in that sense. And very often, symmetry itself gives quite a strong constraint on how a neural network is supposed to look like. If you actually go back to this representation of a graph neural network, it's actually an application of that, because we know that in a graph neural network, the order of the nodes is immaterial, right? So there's actually a group symmetry there. If we permutate any nodes in any way, so there's a permutation group, we know the outcome should be the same. You can actually show that this is the most generic case of an element of an operation that fulfills this. And this study is still relatively new, but the idea is that if we understand how we can best incorporate groups into these neural networks, we can classify neural networks a lot better, and we can be much more targeted at finding what is the right neural network to take for any particular problem.
I guess you can think of the football pitch like you can rotate the pitch however you want.
Yes.
It's the same GNN, right? Except you don't want it to be the same. If you rotate it, you want the features to change because left and right.
Yeah, but if I take any GNN and take any node features and I rotate it, meaning I flip on every input feature, say the x-axis, my normal GNN would give a different answer, right? Because it has no way to enforce the symmetry. And now the idea is, with this geometric deep learning, what do I have to do in order for this symmetry to be naturally fulfilled in my my machine learning?
So you are modeling x coordinates, not distances between nodes. You're modeling them with their coordinates.
In this particular symmetry, right. Is this a particular application? Yes, but this is actually a very generic thing, and it's again it's one of the founders of this is Max Welling. You know he is very famous papers, and turns out that his PhD supervisor was Van 't Hooft, who is a Nobel laureate in physics, who did something very, very similar to physics. But you take a physical theory, you assume some symmetries and see how far can you push it and what can you get out of it. And clearly, what he did was somewhat right to get a Nobel Prize for it. So it's a very, very fruitful approach to this sort of problem. And generically, when we say symmetry here, we would say that if G is any group, and I apply this group to my my node inputs, my edges, and the global feature vector. I want that the output is independent of it. It should be the same as if I wouldn't have had the group applied in the first place, and that should be true for any element of that group. So that in this particular case, it means if I take any of my 4 actions, of course, one is trivial, it's just the identity, but if I flip it, I want that the output is still exactly the same. Yeah, as I said before, GNNs themselves are an application of this because they are specifically designed to fulfill this node permutation symmetry. In our problem here, we know that we do know how the group acts on the spatial features, right? So for the x and for the positions and for velocities, we just put a minus in front of the either x coordinate or the y coordinate, or for the flip, for the double flip, it would be a minus in both. And now the question becomes, how do we actually enforce this approach? Now, one approach is to just take whatever model you train, and we know this model is not, wouldn't enforce the symmetry, but what I can do is I can take my inputs, rotate them, and run the model again and again for every member of my group, and just average the outputs, and thereby I would have made an invariant predictor, right? So now if I take this object here, and you can easily show that if I were to rotate x and e and g by yet another member of the group, say h, gh is still a member of the group, and because we sum over all the group members, essentially what we do is we do nothing, and that thing is truly invariant. And another approach to do this would be to just take our inputs and take an average, for example, of all their, or a concatenation, or an average of all their different rotation, and then train the models on that. That would be another way of sort of enforcing the symmetry. Now here, what they do is they rely on yet another paper, and that is called group convolutions. And they took inspiration essentially from convolution operations in images, right? Images actually, how did people come up with convolution operations? It's actually also a symmetry consideration that if I take a picture and move it up or down a little bit, it should get the same thing. So, and I think it was Jan LeCun who was saying, okay, how does my layer have to look like in order to be invariant under small movements up or down? And so he came up with this convolution network, right, which has a small kernel and effectively just averages or weights neighboring pixels, and because it moves over the whole thing, it sort of abstracts this away. And these group convolutions are a abstraction of that, where instead of taking the translation group, so the movement in the plane, they take a very generic group and say, okay, when is my network sorry, I probably should take a step back. What is actually what's wrong with this? In one case, in the first step, we just learn a full model and average afterwards. That seems sort of wasteful because the model itself has never really experienced the symmetry. Very similar to if you symmetrize the inputs, right? The model does not really see symmetry at any point in time. And what we want is something where inside the model we sort of carry symmetries around. And what we say is that if I take any layer and apply the symmetry on that layer, it should be the same as if I take as the layer has an input the node representations, the edges, and the global features. If I apply my group operation to each of them, it should be the same as if I take the output of that layer and apply the rotation or group just there. And that is sort of the question: what sort of layer would I get if that sort of enforces this property? It's called equivariance, essentially that the outputs behave similar to the group as the inputs did. And in order to do this, we take, before we had each node had essentially one representation. Now we say we have one representation for each group that is applied to that node. So we essentially, on each internal network representation, we have now four representation of the group, or four matrices where we had before only one, right? And each one of these represents exactly one of the four group elements, say the flip left to right, flip up or down, or flip left, right, up, down. That's a bit, that's quite a lot to sort of swallow in one. Any questions at this point?
So my understanding was that they just that what they did is they fed in the inputs with all four different group members, and then they, I don't know, maybe average the outputs or something like that. But you're saying that's not what they did.
They did, yeah. So they did indeed symmetrize, create the four different rotations of the inputs. But in order to keep the symmetry going through the whole network, they had to keep also these intermediate steps that also have the groups attached to them, essentially. And the only point where the invariance comes from the very final layer, when you take all the different representations and combine them in some way to make your predictions.
So you split it into, you create the four, you put them all the way through.
Yeah.
And then in the last layer, you look at all of them together to come.
Yes.
Okay.
And you allow the network at any point as it walks through to see the different rotated versions of the internal matrices. And so this is the idea of this group convolution, where I convolute not just over, say, as in a normal convolution network, over the X and Y translations, but rather I take a function, I take an input, which is one member of the group. So if you remember, we have four versions. I concatenate each of them with the group inversion and apply this machine. And if I do this for all the group members, so this is like this average, right, where we in the past averaged over all XY coordinates, now we average over all group symmetries. And because we can do this for each group, this G-1 is here for each group, we can get for all of our groups a group, for all of our group members a representation that is shifted. And we can show that if I apply, say, another group move here, that move would just shift through, and that leaves it invariant. This particular form of averaging has this property that if I shift my inputs by a group element, the output is also shiftable. Now, in order to do this, I'm also going to be quite honest with you, I don't quite understand the details of how this and the GATV2 combine, whether they average, whether they have first the different groups averaged and then the attention mechanism, or the other way around. It's not quite clear, to be honest. But how does it in practice? So we know how the input layer looks like, right? So the input layer, we actually know how to perform the groups by just flipping the X and Y coordinates. Later on, if I take anywhere in my network and look at any of the representation or matrices that belong to a particular symmetry element, I would not be able to tell you how to move from one to the other. However, I do know that by this construction, if I want to know what the representation is of the rotated one, I would just look at what is the representation of that group applied to that, right? So if I, yeah, it's hard to explain. This is something we have to think it through, that these, because it's sort of constantly rotating, you always know what would be the output if I would have rotated it, because you can just sort of follow it through, and it works. But yeah, it's something to sort of meditate a little bit about why it works. But it's powerful because it's, again, we allow representations of the symmetries to go through the network, and the model has the time and the opportunity to learn from each of them and combine them at each step. which is quite powerful. And this is how it looks like. And again, as input, so here the part that's missing is essentially where you take the input and apply the symmetry, the 4 symmetry operations, so the identity and plus all the 3 others. That gives you your reflected views and your original view, and then you pass them through here. And at each level, you have the identity encoding, but you also have the rotated views if you want. And only at the very end you combine them and then do whatever you need to do in order to do your prediction. Questions?
Not for me.
Okay. How do you then do the actual predictions? Well, it depends a little bit on what you're trying to predict. So for the receiver prediction, we want to again predict who is going to receive the ball, and there you take. Remember, each input was a node matrix X, but now we have of each of them the flipped version. So we also end up because the number of features doesn't change as we go through the network. So we end up with all 4 representations, so the identity, but also the flipped ones. We can average them out, and then have just a node-wise classifier of this. I guess it's either 11 or 22 nodes. I don't know whether they have some masking in there, on which the model then predicts which one is the most likely receiver of the shot. Very similar for graphs. You take all the nodes, but now you sum over all the players, and then do a prediction on the big concatenation. And this is for the how do you call it, for the recommendations. So for the recommendations, we only have to look at the identity, because if I say, okay, this player has to move, say, 1 meter to the left, in the flipped version, I would have to say he moves 1 meter to the right, right? So it's not an invariant problem, but rather an equivariant problem, that my outputs are the flipped versions of the inputs. And how do we do it here? We essentially have a model that is a VAE on top of the last node representation. So we sort of build a Gaussian envelope around that representation, and then we use a guided generation where we say that we know that if I give it an input, my output of that node should be somewhere in this Gaussian envelope. Now, where in my Gaussian envelope do I have to move my point to, which ultimately filters down to the inputs in order to maximize or minimize the shot? So if you look here, this so the KL, the versions here, make sure that the recommendation doesn't stray too far away from my original input, whereas the first term tries to maximize based on the context, whether a shot happened or not, into what is the X on the input of the on the identity input that sort of maximizes or minimizes that probability. And that can be used then to create this thing. So that is how the whole how they displayed it. So you have your data, you get all the flipped versions of it, pass it to this TacticAI, and that sort of keeps track of all the different representation, and then at the end does the prediction. So that was the hard bit. So now we can talk a bit about what the actual outcomes were from their studies. First thing they did was, did the nodes actually, the embeddings, are the embeddings fundamentally different from the inputs? So here, they this is a TSNE from the input features. So you take of each team. I think red was the attacking team, blue was the defending team. Take each team and average their team members' features, and you would add a dot here. And when you do this, you see that on average, you can't really tell blue and red apart, right? So there's no region in space where it is only blue or only red. So on a pure input space, that the teams are, you can't really separate them on that TSNE plot.
Can I ask a question?
Yeah, please.
Are those embeddings the originally featured features, or after training a GNN?
So this is the original features. Now,
they're roughly equal teams then.
Say again?
So this means they are roughly equal teams.
Yeah, it means that if I tell you that a player is in a position 5 meters away from the goal, 1 meter off the center, it might as well be attacking or defending.
Okay, makes sense.
Yeah. And now what they did, they looked at the the TSNE embeddings of the embeddings that came out at the end of their model. And it's actually quite interesting. You see that red and blue are very well differentiated, right? So you know the embedding is quite different for the defending team and the attacking team. And what's perhaps more interesting is that there's actually a structure to it. So if you look at similar attacks, for example, outswing or inswing, whether the ball moved outwards or sort of was flanked inward, they actually go to different parts of this TSNE embedding space. And so you could argue that it's probably easier to find similar situations by going to lobes in these embeddings to find situations that are similar in terms of what happened in that game. Again, the same is true for attacking or defending team. So that sort of means that the model learned actually a reasonable embedding of something salient, which is cool.
Do you think this is largely because of the loss function?
Say again?
Do you think this is the quality of learning embeddings is mostly because of the loss function?
Yeah.
Because you're assuming that the loss function is whoever receives the ball, right?
Yes. So you make a very good point there, right? So, and I have it a bit later. So in this one, we as an input feature, we don't know who is on which team, right? This is purely just on a node feature. So the node features doesn't have a team feature like attacking or defending. Is just where's the player situated, how tall he is, and whatnot. Whereas the embeddings, they have actually when they pass through the network, they had access to the edge information, and the edge information knows who is at least on the same team. So you could argue that the team that is probably in the corner, in the proverbial corner, is the team that is doing the attacking. So when that passes through the network, it sort of figures out who is on the attacking team based on who is on the same team as the guy who is standing in the corner. And so you could very well argue that the comparison of this feature or this embedding and that embedding is not quite fair, because this embedding had fundamentally more data at its disposal than the other one, based on who is on the same team, right? Yeah, but I think that's it. And probably also it did. I don't know whether the loss function made the difference. You could, in principle, probably write an auto encoder and would probably get similar results, I would think. Not sure. Yeah. Then, so one of the things in the prediction, one is what they try to predict is the top 3 accuracy. They probably took top 3 because it's a difficult problem, and the top 1 accuracy would look a bit too bad. And they compare the different baselines. So I think the very first one is a model that doesn't have this graph neural network structure at all. It just has I think it's similar to the soccer map, where you have like a embedding of the positions of the player, and to do that, and it performs rather badly. So just adding the nodes without even the edges gives a very, very healthy bump in top 3 accuracy. The next step, you add attention to it. That has you add the nodes, the edges to it. So you have like a proper graph, and you already you get a nice bump up. Add attention, you also get an even better jump. And then comes the symmetry application. First case is where you do the frame averaging, right? Remind you, it's where you take all the inputs, flip them, and only at the very end combine the results. So it's take the average probability of all 4 predictions. And that, again, gives a very, very healthy jump in prediction accuracy. And lastly, they tried their version of this group convolution, right, where they keep the symmetry throughout the network, and only at the very end, when they do the prediction, that they make it truly invariant to the symmetry application. Again, it gets a bit of a lift However, if you look at the uncertainties, I don't think you can say that it's actually better than just doing the frame averaging. And given that you essentially, if you think of it, like every node, instead of like one feature set of features or representations, you have 4. You actually build quite a lot bigger network or you have quite a lot more data passing through. So you could very well argue that it's probably not worth the effort compared to just frame averaging to get similar results. They looked at what sort of recommendation does the model give? On the top left corner, you see a typical situation. You see red obviously is in the corner, and I think it gives recommendations for the blue team. So you see for the blue teams, there are these light blue arrows that are slightly shifted from the original team. Then they checked. So what happens in the shifted version? Before you have every attacker essentially gets a probability of them receiving the ball. You have the highlighted 4 here, 1, 2, 3, 4. 4 is very close to the goal, so 3, 2 further away, and 1 very far away. Now in the red picture or in the red bar chart, you see that the 2, 3, and 4 they have the higher probability of receiving the ball from the corner guy, and 1 naturally low. By adjusting the defensive position a little bit, essentially a lot of that probability mass moves to the player that is very far away from the goal. Because he's far away from the goal, the likelihood of a shot is a lot lower. So that is why the model thinks that this is a positive contribution to the team's defense when they do this. They did an analysis. Just quickly skim over this. So they had essentially 3 guys, 3 data scientists, 1 video analyst from football club, and 1 coaching assistant, and they did tests on them, and essentially stuff like, can you tell the difference between what is an original one or an original corner or 1 corner that the TacticAI network has slightly altered to a better recommendation? And they say it's indistinguishable, but statistically indistinguishable. They I can skip over this. Apparently, people had different ideas of how they classified these corners, which is supposed to tell that different humans actually have different preferences. They say that on average, the model is not. Humans are on average as good as predicting on the original as on the generated models. Again, if you look at the plots, they actually look quite different. And what I really didn't like about the paper is that many of the plots they make, they use these violin charts, even though the distribution is very strictly discrete, right? So here they have the average receiver prediction, but if you have only 5 guys, it's a number between 0 and 1. For some reason, they had also a shift in here that one of the reviewers of the papers moaned about, that here the numbers clearly go to 1.2, so something did go wrong, but I think in the final paper they sort of fixed that. But when they say they are statistically insignificant, but then you look at it and it looks quite different, I don't know whether that is very meaningful or just a small sample size issue. Don't quite remember what they did here, but essentially here they say that different people, like you have 3 people who roughly do the same thing, and very likely those are the 3 data scientists that work for the football club. So the football experts seem to be doing something slightly different than the data scientists are doing, which take from that what you want. And then the question is, are the generated samples helpful? Like the tactical corrections, are they considered helpful? And most of the 5 people would say that yes, it is ever so slightly better than the original corner. But the so this was a corner retrieval. How good is the situation at retrieving corners that are similar? And here again, most people agree that the TacticAI gives the better corner retrieval, meaning that if I give it a corner, it returns me another corner that is similar in this embedding space, and that looks better than if I were to just take the cosine feature space similarity. That, however, again has the same flaw that of course, one uses the edge information, the other one doesn't. So comparing them like this, in my opinion, is not fair. And probably, if I were to add the corner information, add the edges to the original data, then the cosine similarity probably would do quite well on its own. And then, sorry, yeah, most people again preferred the TacticAI recommendation, but only sometimes for sparking discussion of what aspects of the defense maybe the discussion hasn't touched yet. So and they also do say that the feature that Jenny picked up, like where does a goalkeeper sit, and should a player follow another or man mark, or these kind of things. These are generally features that also a football expert would have in their mind when they discuss tactics. So there seems to be generally something there in the model that gives value, and I think that is ultimately what they were looking for. And yeah, again, it's more to stimulate discussion than anything else. Also, what I found quite interesting is that they could, because you can apply it week by week, you can sort of see players who might take coaches' advice better than others, and you can, they call it targeted intervention. I mean, coach is going to yell at them or something, but they say that is helpful. And yeah, that's it. So we have a model. It predicts shots, and who receives a corner, who makes a shot attempt, and nudges it into recommendations that supposedly make it helpful, and people say, experts say it looks good. That's it. Thank you very much.
Thank you.
Thanks, Arvind.
Any questions? Sorry, we ran slightly over time.
Sorry, I had so many questions.
Okay, well, I guess we'll finish it there. Thanks, Arvind, for presenting. Really cool paper.
Thank you.
It will be interesting. I think maybe it's like a beginning of more of an application of this type of machine learning to sports. So we'll have to see where it goes.
I almost think it might be getting more use also outside of sports, where you have these symmetries. It's just in sport, you're sort of lucky that you play it on the same pitch, right? So your data is a lot easier to enforce these symmetries, whereas wild data might not have that generally. Again, these node permutations is a quite strong symmetry that's why graph neural networks are quite common, but but actual physical symmetries, so it's a lot harder to come by, I think.
Yeah, true. Okay, cool. Well, let's end there, and thanks everyone for coming.
Yep. See you next time.
Yeah.